Hi guys, my name is Ken Jing Hang, who is Group 4 leader. We are going to present for our group project to all of you with the title of Effect of Altitude in the Performance of a Spark Ignition Internal Combustion Engine. First of all, I'm going to introduce my group member. The first profile picture is me, and then the second one is Tang Zhengyi, followed up by Chia Wei Yi, and then it comes to Yi Chi Wang, and the last is Maheshan Analaki Ravi. Introduction. Let's come to introduction. For problem statement, the first one is how the altitude variation is important on the condition of the spark ignition internal combustion engine, and then is followed up by how does the change of altitude effect on spark ignition engine performance. The objective of this project is to identify the relationship between the condition of the spark ignition internal combustion engine and variation of altitude. The second one is to identify the performance of spark ignition engine when it located at different altitude level. Significance of the project is to understand the behavior of engines at altitude and facilitate automobile diagnosis. Basic principle of the system. Otto cycle is an idealized thermodynamic cycle that describes the functioning of a typical spark ignition piston engine. Otto cycle consists of isentropic compression, which is from phase 1 to phase 2. If you look at the right bottom, the graph at the right bottom there. And then it comes to heat addition at constant volume, which is from phase 2 to phase 3 with delta V equals to 0. V represent the change, delta V represent the change in volume. And then it comes to isentropic expansion, which is from phase 3 to phase 4. And the last is rejection of heat at constant volume, which is from phase 4 to phase 1 with delta V equals to 0. My pass comes to the end. I pass my turn to my friend, Maheshan. Thank you.
Schematic and drawing diagram. Let me briefly explain the function of each part. Crankshaft, responsible for the proper operation of the engine and converting a linear motion to a rotational motion. Spark plug, to form a spark for igniting the air-fuel mixture. Top dead center, TDC, the position of piston at the very top of its stroke. Side cylinder, a chamber where fuel is combusted and power is generated. Board dead center, position of piston at very bottom of its stroke. Piston, to seal off the pressurized combustion chamber from the crankcase. Connecting rod, it connects the piston to the crankshaft to the transfer combustion pressure to the cranking.
Okay, so now I would like to present about the method of performance analysis. Okay, this project of the experiment is to go through the evaluation of the behavior of the variables of a spark ignition engine. Like example, such as engine rocker, injection power valve, MAP sensor voltage, TBS sensor voltage, and intake manifold exhaust pressure. Okay, the tests are conducted at different altitudes with different or approximately 500 meters from sea level to 4,500 meters above sea level, with the engine running at ideal and at different resolution. Okay. The engine vacuum volume are monitored in the intake manifold with a vacuum gap. The external vacuum index must be added. Okay, so here is the example of our method of performance analysis. First, we're going to prepare measuring instrument. Second, turn gear off. Third, key on, engine off. Number 4, turn engine and maintain in ideal. Number 5, accelerate to 1,800 rpm and stabilize. Number 6, return to ideal. Number 7, accelerate to 2,500 rpm and stabilize. Number 8, return to ideal. Number 9, accelerate to 3,500 rpm and stabilize. Number 10, return to ideal. And the last one is turn gear off. Yeah, I think that's all for me. But I would like to pass to my member to the coming part. Thank you.
This is a performance calculation of the system. There is an adiabatic relationship between atmospheric pressure, the vacuum pressure in the intake manifold, and the absolute pressure of the intake manifold, always maintaining this when the engine is idling. By using formula, atmospheric pressure equals the vacuum pressure in the intake manifold plus the absolute pressure of the intake manifold valued by the MFP. The MAP sensor evaluated shows a variation in their measurements. However, the behavior is similar in the operation of the engine at different revolutions. So under this result, the automotive diagnosis can be performed on any vehicles and not specifically for each vehicle brands. The graph 1 shows a variation of the absolute pressure registered by the MAP in the scanner at different revolutions for each height. The highest MAP vacuum is 27 kPa at 0 MASL, and when the car engine is at 700 RPM, while the lowest MAP vacuum is at 18 kPa at 4000 MASL when the car engine is at 3500 RPM. MASL stands for high above sea level. Next, the graph 2 shows the MAP sensor voltage variation at different altitude for 0 RPM. The voltage is in a decreasing order when the altitude is increasing. Last, the graph 3 shows the vacuum ratio, MAP, atmospheric pressure at idle.
Hello everyone, I'm Yi Chi-wei, and I'm going to present about the suggestion of system improvement. The first suggestion is to use of turbocharging and supercharger. Turbocharger. A turbocharger is a turbine-driven forced induction device. It consists of turbine and compressor coupled to a common shaft. The potential of higher power with turbocharging leads to engine downsizing to improve fuel economy while maintaining driving performance. Turbocharged engines do not suffer a dramatic reduction in power since the turbocharger is more capable for pumping thinner air, and they are effective at high altitudes. Supercharger. The supercharger is also known as forced induction system. Supercharging has a significant effect on the power output because it is possible to get higher values compared to the naturally aspirated engine. The second suggestion is direct fuel injection, or normally known as DFI. In DFI, the fuel is injected directly into the combustion chamber inside the cylinder at very high pressure, and the combustor mixture formation takes place almost exclusively in the combustion chamber. DFI also allows gasoline and diesel engine to burn less fuel and give precise control over the timing and the amount of fuel which is injected. The use of this system provides better cylinder charging, higher compression ratio, reduced knock sensitivity, higher pressures, certified charge injection at startup, multiple fuel injection, and etc. It also provides lean burns as well as increased engine performance, fuel economy, and reduced emission levels. The third suggestion is low temperature combustion (LTC). Low temperature combustion (LTC) engines have potential to deliver higher fuel conversion efficiency and simultaneous reduction of nitrogen oxide and shoot emission to an ultra-low level. LTC also reduce the heavy dependence of nitrogen oxide and shoot after treatment device for meeting the emission norms. LTC approximates a constant volumetric combustion in very short combustion duration, and it can achieve for high compression ratio. Therefore, it results in higher thermal efficiency. The fourth suggestion is water injection. Water injection considered as an advanced technique that relies on injecting fine spray of water into the intake port. It also viewed as one of the possible solutions for many problems in internal combustion engines since it promised to make the engines operating with larger compression ratio and stoichiometric combustion at high load, resulting in a drop of the specific fuel consumption on the overall engine map. Coupling water injection with VCR and co-EGR technologies provide very good results and characteristics, where VCR can compensate for higher knock limitation with a lower compression ratio if water injection cannot be used due to lack of water or at low ambient temperature. Lastly, the suggestion is run the engine at optimum condition, which means that the engine will run in low friction and low pumping work. That's all from us. Thank you.